Okay, today I want to go over 4.4, which is about L'Hopital's rule. So let's recall things before we get into L'Hopital's rule. So remember how we did the limit as x goes to 2, x squared minus 4 over x minus 2. So we would get 4 minus 4 is 0 over 0. Say factor it, because it's factorable, we could do that. And then we reduce the x minus 2 and then apply the limit. 2 plus 2 is 4, and that's the end of it. Also, we did see that the limit as x goes to 0 of sine x over x is 1. I showed you that using the t-table. Also, when we have, say, limit as x goes to infinity of 2x squared minus 3 over 3x squared minus 5x plus 1, which is infinity over infinity, and we said if x goes to infinity, we only do the leading terms, so 2x over 3x squared, which is 2/3. Okay. What about if we have indeterminate form like 0 over 0 over infinity, and it's none of these that where we could factor or rationalize or cancel things out? What about something like the limit as x goes to 6 of ln of x minus 5 over x minus 6? So we get ln of 1 is 0, 6 minus 6 is 0, and we can't factor, we can't rationalize, so we're stuck. So for something like this, this is 0 over 0, which is what we call indeterminate form. But it cannot be done using the old technique where we can factor or rationalize or all that. How about also something like this, x to infinity, ln of x over e to the x, which is infinity over infinity. Again, another indeterminate form. So what do? We use what we call L'Hopital's rule. It's a new technique. It's a lot easier than anything else that we've learned. L'Hopital's rule, which uses the derivatives. So suppose that f and g, so there are two differentiable functions, and g prime of x is not 0. You will see why, because we're going to have this in the denominator on an open interval containing I. And open interval I contains a, except possibly at a. Suppose also that the limit as x goes to a f of x equals 0, the limit as x goes to a g of x is 0, or the limit as x goes to infinity f of x, a f of x is plus or minus infinity, and limit as x goes to a of g of x. So you're going to talk about 0 over 0 or infinity over infinity. Then if you're doing the limit as x goes to a f of x over g of x, and you're getting 0 over 0 or infinity over infinity, okay, if you're getting 0 over 0 over, you can do the limit of f prime of x over g prime of x, and that's going to give you the same answer. Okay, that's going to give you the same result, which is pretty neat. I am looking at the examples right here. So remember how we did this by factoring and we got 4. So if we get 0, 0, we can do derivatives here. So it would be what? 2x over 1. 2 times 2 is 4. So the answer is 4. Sine x over x. Again, this is 0 over 0. So if you do the derivative, it's cosine x over 1, cosine 0, which is 1. Pretty neat, huh? Same thing here. It would be 4x over 6x minus 5, which is still infinity over infinity. We do derivative again. 4 over 6, which is 2/3, right there. Okay. When can you use L'Hopital's rule? Whenever you have 0 over 0 or infinity over infinity, you can do the derivatives. It doesn't just work for a, it works for x goes to a minus, a plus, or plus or minus infinity. So you can use any of these, any a, okay? So for number 10, page 16, what's the limit as x goes to negative 2, x cubed plus 8 over x plus 2. If you put a negative 2 in there, we get negative 8 plus 8 over negative 2 plus 2, which is 0 over 0. So that's one of the indeterminate forms. We could do factoring like before, or we could do L'Hopital's rule. Derivative of x cubed is 2x squared over 1. The limit as x goes to negative 2, which is 2 times negative 2 squared, which is 8. Oh, it's 3x squared, sorry. So 3 times negative 2, which is 12. My bad, okay? Derivative of x cubed is 3x squared. Alright, number 14 from page 316. Limit as x goes to 0 of tangent 3x over sine 2x. Again, we plug the 0 in, we get tangent 0 over sine 0. 0 over 0 with indeterminate form. So we do derivative. Derivative of tangent 3x is secant square 3x times derivative of 3x, which is 3. That's cosine 2x times derivative of 2x, which is 2. If we put the 0 in there, 3 secant square 0, which is 3 times 1, 2 cosine 0, 2 times 1, which is 3 over 2. Now sometimes it's a lot more work than this, like 26. No, let's do 18, I'm sorry, and then I'll get to 26. Page 316. Limit as theta goes to pi of 1 plus cosine theta over 1 minus cosine theta. So if we plug 0 in for, pi for the theta, 1 plus cosine pi, negative 1, and 1 minus negative 1. So it's 0 over 2, which is not indeterminate, it's 0. So there's not any need for any other rule, let alone L'Hopital's rule. So you're not going to always do L'Hopital's rule. If you answer, you're done. Okay, 26, page 316. The limit as u goes to infinity, e to the u over 10 divided by u cubed. So if we put infinity over any number is infinity, e to the is infinity, infinity cube is infinity. So this is indeed indeterminate form. So now we're going to do derivative. So the limit as u goes to infinity, derivative of e to the u over 10 is e to the u over 10 times the derivative of u over 10, which is 1 over 10. Derivative of u cube is 3u squared. So this is the limit as u goes to infinity of e to the u over 10 divided by 30u squared. I did the 10 at the bottom times 3u squared is 30 u squared. So 30 is a constant. We can move it out. 1 over 30. The limit as u goes to infinity. Now we do the derivative again because we have what, infinity over infinity. So again, it's e to the u over 10 times that, derivative of that, and then u squared is 2u. So again, the 1 over 20 times 1 over 30 is 1 over 600. Limit as u goes to infinity e to the u over 10 over u, which is infinity over infinity. One more derivative. Again, it's 1 over 10 e to the u over 10 divided by 1, because derivative of u is 1, which is 1 over 6,000. 10 times 600 is 6,000. And then e to the infinity is infinity, which is infinity. So it took us a couple of derivatives, couple of steps to get the answer. Okay. 32, page 317. So what's the limit as x goes to infinity of ln of x squared over x? Again, we always try to do it without any rules. We put infinity in there, so we get ln of infinity is infinity. Infinity to any power is infinity over x is infinity. So it's indeterminate rule. So we do L'Hopital's rule. We find the derivative of ln x squared, which is 2 ln of x, times derivative of x, which is 1 over x. Okay, times derivative of ln of x, which is 1 over x, and then derivative of x is 1. So this is the limit as x goes to infinity, 2 ln of x over x, which is still infinity over infinity. We can pull the 2 out, it's a constant. Now we're going to do the derivative again. Derivative of ln of x is 1 over x. Derivative of x is 1. So it's 2 times over infinity. 2 times 0 is 0. Alright, here's another example. This is not from the book. Limit as x goes to 0 of e to the x minus e to the negative x minus 2x over x minus sine x. If we plug the 0 in, e to the 0 is 1, minus e to the 0 is 1, minus 2 times 0 is 0, 0 minus sine 0, so we get 0 over 0, which is indeterminate. Now we're going to do derivatives using L'Hopital's rule. So we're using L'Hopital's rule. So derivative of e to the x is e to the x minus e to the negative x is e to the negative x times derivative of negative x, which is negative 1, minus derivative of 2x is 2, derivative of x is 1, derivative of sine x is cosine x. Remember, we're not doing the quotient rule. We're doing derivative of the top, derivative of the bottom. Okay, big difference. It's a lot easier too. So this is the limit as x goes to 0, e to the x plus e to the negative x minus 2 over 1 minus cosine x. So let's plug the 0 again. So we get 1 plus 1 minus 2 over minus cosine 0 is 1. We still have 0 over 0. So we're going to do L'Hopital's rule again. So I'll just write HR. That means we're using L'Hopital's rule again. So the limit as x goes to 0, e to the x is e to the x. Derivative of e to negative x is e to the negative x times negative 1. That's why I have a negative here. Derivative of 2 is 0. Derivative of 1 is 0. Derivative of cosine is negative. Sine times negative is sine x. Again, do it one more time. So we get 1 minus 1 is 0 over 0. Again, L'Hopital's rule. Third time. Limit as x goes to 0, derivative of e to the x is e to the x. That's e to the negative x times negative. That makes it a positive. Derivative of sine is cosine. If we put a 0 in there, 1 plus 1 over 1, which is 2. So sometimes it's a few steps before you can get the answer. So don't give up and be patient. Okay. So now let's go over other indeterminate forms. Okay, the indeterminate forms that we talked about were 0 over 0 or infinity over infinity, plus or minus. Okay, other indeterminate forms, there are indeterminate products. So if the limit as x goes to a, f of x equals 0, and the limit as x goes to a, g of x equals plus or minus infinity. That means the limit as x goes to a of f of x times 2x, you're getting 0 times plus or minus infinity. So this is indeterminate. We don't know what the answer is the way it is, so we have to work it out. What we can do, we can fix it by writing, let's say it's 0 times infinity. You can write 0 because you can write 0 times infinity as infinity over infinity or 0 over 0. Why is that? Because 0 can be written as 1 over infinity times infinity, or infinity can be written as 1 over 0 times this 0. So that's what this is coming from. Okay? So here's an example. 44, page 317. The limit as x goes to infinity, square root of x times e to the negative x over 2. So square root of infinity is infinity times e to the negative infinity, which is 0. So it's infinity times 0, which is indeterminate form. To fix it, so we can use L'Hopital's rule. We're going to write this as a limit as x goes to infinity, square root of x. Instead of having e to the negative x over 2, we write it at the bottom as e to the x over 2, and now we have infinity over infinity. So we basically changed the 0 into 1 over infinity by putting this under 1. Okay, that's what we did. So now we're going to do L'Hopital's rule by doing the derivative of square root of x, which is, square root of x is x to the 1/2, so it's 1/2 x to the negative 1/2. Derivative of e to the x over 2 is e to the x over 2 times derivative of 1/2 x is 1/2. The 1/2 cancels out. And you get limit as x goes to infinity. So we can put x to the 1/2 at the bottom, square root of x, e to the x over 2. Now if we do infinity, we get infinity times infinity under 1. 1 over infinity is 0. And another example, just to demo this, number 50, page 317. The limit as x goes to pi over 2 from the left of cosine x secant 5x. So if we put that in, cosine pi over 2 is 0, secant 5 pi over 2 is infinity, so it's indeterminate. So to fix it, we're going to change secant into 1 over cosine 5x before we can use L'Hopital's rule, because we can only use L'Hopital's rule if it was a quotient. So it's cosine x over cosine 5x, and you can see now it's 0 over 0. So we can do the derivative using L'Hopital's rule. So the limit as x goes to pi over 2 from the left, the derivative of cosine x is negative sine x, and that's negative sine 5x times 5. The negatives cancel out, so sine pi over 2 is 1 over 5. Sine 5 pi over 2 is negative 1, so we get no, it's 1, sorry. So we get 1 over 5. Okay. So we've seen 0 over 0 indeterminate form. We've seen infinity over infinity. And then we've seen 0 times infinity. Next, we're going to see indeterminate forms. Indeterminate differences. Okay, indeterminate differences. So if the limit as x goes to a, f of x equals infinity, and the limit as x goes to a, g of x equal infinity, then the limit as x goes to a, f of x minus g of x, infinity minus infinity, which is indeterminate. So to fix this, it's not as easy to fix it. Convert the difference into a fraction. Why fraction? Because we want to get 0 over 0 over infinity to use L'Hopital's rule. Using, LCD, least common denominator, rationalizing the denominator or numerator, or factoring out common factor. We don't know, depending on the problem. Okay, so if you have a infinity minus, if it was infinity plus infinity, that would be infinity, we're done. If it was negative infinity minus infinity, that's negative infinity, which is done. Infinity plus infinity is done. But if you have positive infinity minus infinity, it's on indeterminate. Okay, so 54, page 317. What's the limit as x goes to 0 from the right? 1 over x minus 1 over tangent inverse of x. So it's 1 over 0 minus 1 over tangent inverse of x is also 0. How? Because tangent inverse of 0, if we let this equal u, then tangent u equals 0, and you're looking only from negative pi over 2 to pi over 2, so u has to be 0. That's where this came from. So you get infinity minus infinity. Okay, and that's why indeterminate. So we're gonna fix it by the best thing to do here is find the LCD, which is x tangent inverse x. So this would equal the limit as x goes to 0 from the right. The LCD is x times tangent inverse x, and then we times this by tangent inverse x, top and bottom. We times this by x, and we get 0 minus 0, and then 0 times 0, and now it's 0 over 0. We can use L'Hopital's rule. Okay, so this is one of the more difficult ones. Limit as x goes to 0 from the right. Derivative of tangent inverse x is 1 over 1 plus x squared, minus derivative of x is 1. And here we have to use the product rule. So we fix x times derivative of tangent inverse is 1 over 1 plus x squared, plus we fix tangent inverse x. Derivative of x is 1. So let's see what we got. So we have so this is the limit as x goes to 0 from the right. We have, let me clean it up a little bit, 1 over 1 plus x squared minus 1, and then x over 1 plus x squared plus tangent inverse x. We have a complex fraction. I want to get rid of these simple denominators, so we're going to times everything by 1 plus x squared over 1. We're going to do the same thing here, and that's how we keep the balance of the fraction, and we can get rid of all these secondary fractions. So this is the limit as x goes to 0 from the right. 1 plus x squared times 1 over 1 plus x squared is 1, minus 1 x squared times 1 is 1 plus x squared in parentheses. This guy times x over 1 plus x squared is x, plus 1 plus x squared times tangent inverse is 1 plus x squared tangent inverse. So we distribute the negative, so we get the ones cancel out, so you get negative x squared over x plus 1 plus x squared tangent inverse x. Alright, so let's apply the 0 again. Well, it's not a magic bullet, so we still get 0 over 0, so we have to do L'Hopital rule again. That's what I was saying. So limit as x goes to 0 from the right. Derivative of negative x squared is negative 2x. Derivative of x is 1. Now here is the product rule. So we fix 1 plus x squared, times it by the derivative of this guy, which is 1 over 1 plus x squared, plus tangent inverse x times derivative of 1 plus x squared, which is 2x. And I put it up front. This guy cancels this out. So we got limit as x goes to 0 from the right, negative 2x over 1 plus 2x tangent inverse of x. It's 2. 1 plus 1 is 2. Sorry, should be a 2 there. All right, that's a 1 and that's a 1, 2. Okay, so now if we put it in, put the value of the limit in, what do we get? So we get negative 2 times 0 is 0 over 2 plus 2 times 0 times 0 is 0. Wow, good for us. 0 over 2 is 0, and that's the answer. Okay, so we've seen 0 over 0, infinity over infinity, and then we've seen infinity times 0, plus or minus, and then we've seen infinity minus infinity. Next, we're going to see indeterminate powers. So if the limit as x goes to a, f of x to the power g of x equals 0 to the power 0, so if both limits are 0, or the base is infinity and the exponent is 0, or the base is 1 and the exponent is infinity, then how do we fix this? To fix it, we either take the ln, okay, remember ln of both sides, or sometimes write, see that expression, f of x to the power g of x as e to the ln of f of x to the g of x, which would be e to the g of x ln of f of x. Why is that? Because we know that e to the ln of u to the r equals e to the r ln of u, okay? And we also know that e to the ln u to the r equals u to the r, because e and ln cancel each other out. That's why we can do that. Okay, so here's an example. So if I want to do, say, the limit as x goes to 0 of x to the power x, well, we get 0 to 0, which is that. So we're going to do ln, because I want to bring the power up front. So if I let y equals x to the x, then ln of y equals ln of x to the x, which is x times ln of x. So remember, my objective is to find the limit of x to the x, which is the limit of y, but I want to do limit of ln of y first, then I will get y. So it's limit as x goes to 0, x ln of x. So I'm doing the limit of this guy, which is exactly that guy. If I do 0, it will be 0 times negative infinity, which is indeterminate. And remember what we did for that? We wrote it as a fraction. So we would write this as limit as x goes to 0, ln of x. Instead of times x, we write it as divided by x. And now it's negative infinity over infinity. And now we can use L'Hopital's rule. Using L'Hopital's rule, so it's the limit as x goes to 0, derivative of ln of x is over x, derivative of 1 over x is negative 1 over x squared, which would be the limit as x goes to 0. Instead of dividing, we're going to times by the reciprocal of this guy, which is the limit as x goes to 0 of negative x over 1, which is 0. So we found the limit as x goes to 0 of ln of y equals 0, but this is not what we're looking for. Okay, let me repeat this. Let me go over this more. It's very delicate. So I wanted to find the limit of x to the x as x goes to 0. So I got 0 over 0, which is indeterminate. So I don't want to do x to the x because I don't know what it is. So I want to write it as y equal x to the x and do ln of that. And hopefully that will be easier. So I did ln of y, and it's ln of x. We can bring that up, x ln of x. To do the limit, we get 0 times ln of 0, but ln of 0 is negative infinity, so we get another indeterminate form, and we know what to do to that. Write it as a fraction. So instead of I doing ln of x times x, I did ln of x divided by 1 over x, which is exactly this. That's still negative infinity, and 1 over 0 is infinity. It's indeterminate form, but now I can use L'Hopital's rule. Okay, there I couldn't use L'Hopital's rule because it has to be infinity over infinity or 0 over 0. Derivative of ln of x is 1 over x. Derivative of 1 over x is negative 1 over x squared because that's x to the negative 1, which is negative x to the negative 2, which is that. So instead of dividing, we times by the reciprocal, we get negative x over 1. The limit of 0 is 0, but this is ln of y. We want y, right? We want the limit of x to the x. If ln of y is 0, if ln of y equals 0, then we do e to the ln of y equal e to the 0, which means y would be what? 1. And that's what we want. So the limit as x goes to 0 of x to the x is 1. Okay? So when you do ln at the end, you have to get whatever answer and put it as a power for e. And that's going to be your answer. As a power for e. Alright, one more before we get to 4.5. 64. Page 317, number 64. The limit as x goes to infinity of x to the power e to the negative x. So if we do the math here, we get infinity, and then e to the negative infinity is e to the 0 is 1 over e to the infinity, which is 0. And that's indeterminate form. So we're gonna again do the same. Y equals x e to the negative x, and then do ln of both sides. So ln of y equals, this goes up front, e to the negative x times ln of x, which I would write right away since it has a negative exponent. I would write it like this. And if I want to do the limit as x goes to infinity, that's going to be infinity over infinity. Now we're going to use L'Hopital's rule. Derivative of ln of x is 1 over x. Derivative of e to the x is e to the x. So this is limit as x goes to infinity, 1 over x e to the x, which is 1 over infinity, which is 0. So we found that ln of y equals 0, so y equals e to the 0, which is 1. And that's it for 4.4. Please review all these rules and make sure you know how to deal with each and every one of them.